Okay, another video. Again, yes, but this one's quick and fast. So, second fundamental theorem of calculus. If f is continuous on an open interval I containing a, then for every x in the interval, the derivative of the integral from a to x of f of t dt is just f of x. You remember how the derivative of an integral, those are inverses and they undo each other, and we would just get the function? Well, that still happens. See, it's just equal to the function. But if you will look, this integral is from a to x. So we're going to a variable. So what happens with this f of t dt is it becomes f of x. And this is just the second fundamental theorem of calculus. So example 7 says evaluate the derivative with respect to x of the interval from 0 to x of the square root of t squared plus 1 dt. So in order for us to use the second fundamental theorem of calculus, several things need to be happening. We need to be taking the derivative of an integral. Check. Our integral needs to be going from a number, see they had the a here, to a variable. Check. And they need to have switched the variable in the function. So since those things happen, according to the second fundamental theorem of calculus, this f of t dt is just now f of x. So all I do is I write what the function is, but instead of the t, we put the x. And that's it. That's it. That's the second fundamental theorem of calculus. Example 8. We have capital F of x is equal to the integral from pi over 2 to x to the third of cosine of t dt. Well, it sure would be nice if I could use the second fundamental theorem of calculus. Instead of that integral f of x, that capital F of x, why don't we take the derivative of both sides with respect to x? And then let's do it on this side also. So I know when I take the derivative of an integral, remember capital F of x is standing for the integral of little f of x, they undo each other and I get little f of x. And now this looks like the second fundamental theorem of calculus. In fact, that's why we did it, right? We're doing the derivative of an integral, check. My integral is going from a number to a variable, check. And my function is written with a different variable as the one in the limit of integration. So check. So we can do the second fundamental theorem of calculus, which says that this cosine of t is replaced with the cosine of the x. But we do have to do something before we can jump straight into it. Getting ahead. We need to rewrite this. Since we wanted that to just be x, but it's x to the third, we're going to do something kind of tricky. It's called u substitution. Our entire 4.5 section is about u substitution. So we're going to let u be x to the third. So then this is the derivative with respect to x of the integral of pi over 2 to u of cosine t dt. Everything is still great for the second fundamental theorem of calculus. The derivative of an integral, we're from a constant to a variable, and my function is a different variable. So it is cosine u, but because we did that u substitution, we've got to do times du dx. Okay? So now we'll go back up here to our u substitution. If u is x to the third, then du dx says take the derivative of u with respect to x, and it's 3x squared. So this is cosine of u times 3x squared, which we'll probably write the 3x squared first. And instead of writing u, we'll go ahead and back substitute and put the cosine of x to the third. There's a little more to that one. I'll go over example 8 again with you in class tomorrow if you ask. But now I think you're ready to handle the second fundamental theorem of calculus problems, 81 through 86. I think you're all set.